Modern physical and digital environments operate entirely on linear algebra mechanics. Every structural shift and simulated motion relies on specific matrices calculating variables in real time. These systems function by continuously mapping inputs to outputs, turning raw numeric coordinates into simulated realities or engineered actions. Mapping data forward is an established, straightforward process. The true engineering challenge lies in reversing a complex system, which requires a highly specific mathematical property. We see this challenge when unprojecting a flat 2D screen coordinate back into 3D world space, or when tracing an aircraft's flight sensor data backward to a fixed global origin. Looking at this schematic, we see the mathematical equation governing this exact reversibility, the identity matrix and the concept of matrix inversion. However, invertibility is not guaranteed for every system. It is a structural privilege strictly governed by a single definitive scalar value. That critical metric is called the determinant. Mastering the mechanics of the determinant provides the diagnostic foundation for controlling, diagnosing, and reversing systems across all major engineering disciplines. We establish our baseline by organizing a system's variables into a standard 3x3 square matrix, creating a conceptual container for the data. This diagram shows the method used to extract the determinant. We execute an extraction algorithm known as Laplace expansion. The algorithm begins by targeting the first row and isolating the primary scalar, A11. We then eliminate all intersecting data in that specific row and column. The remaining values form a 2x2 minor matrix, which we multiply against our isolated scalar. Expanding this process across the entire top row yields the full algebraic formula. The rule strictly enforces alternating positive and negative signs between each term. While these steps are algebraic, the resulting scalar defines a geometric magnitude. It acts as a multiplier, calculating exactly how much the matrix scales or transforms the volume of the space it acts upon. This leads to the structural requirement for invertibility. A matrix is only non-singular if its determinant does not equal 0. A determinant of 0 means the matrix mechanically collapses space entirely. All distinct points merge, destroying the underlying information and making mathematical reversal impossible. Other core operational properties scale from this rule. Transposing a matrix preserves its exact determinant, while any identical rows within the matrix will automatically force a 0 determinant. Calculating this single scalar acts as the ultimate diagnostic gatekeeper. It instantly proves whether an engineering system is structurally sound before any further processing demands are placed on the hardware. We see this applied immediately in aerospace engineering and physical telemetry. A spacecraft must continuously track its orientation in relation to an external coordinate system, like an Earth-centered inertial frame. Flight systems map this rotational orientation using distinct arrays known as direction cosine matrices. Because physical objects cannot spontaneously change their volume or handedness in reality, the determinant of a valid rotation matrix must equal exactly +1. If the math returns a determinant of -1, it mathematically represents a physical reflection. For a solid spacecraft, this is an impossible physical state, instantly signaling a critical system error. When flight software needs to reverse a coordinate transformation, mapping local sensor data from the body frame back to the global frame, it calculates the exact inverse of that rotation matrix. Because rotation matrices are structurally orthogonal, the inverse is simply equal to the transposed matrix, providing a highly efficient computational shortcut for real-time flight software. In attitude kinematics, the determinant enforces strict physical reality, while mathematical inversion translates telemetry bidirectionally, without losing data. We observe the exact same dependency when shifting from macroscopic aerospace systems to the microscopic flow of electricity in circuit networks. Circuit simulation software models massive networks of resistors and capacitors by formulating simultaneous linear equations via Kirchhoff's current law. This schematic illustrates the mathematical structure governing circuits, the equation Y times V equals I, where Y is the nodal admittance matrix. To solve for the unknown voltage vector V, the simulation must multiply the source current by the inverse of the admittance matrix. Finding this exact steady-state voltage distribution across complex meshes is completely bottlenecked by the structural invertibility of Y. If the determinant of the admittance matrix equals 0, the calculation breaks. In physical circuit terms, a mathematical zero indicates an ungrounded, floating, or physically unrealizable network. It lacks a unique solution. In electronics, a singular matrix is the mathematical demonstration that the designed hardware cannot exist in a stable, closed-loop physical state. The constraints of the matrix carry directly into computer science, specifically within the architecture of 3D rendering pipelines and game engines. Modern game engines rely on affine transformation matrices to scale, rotate, translate, and ultimately project 3D models onto a flat 2D screen. These specific volumetric changes are driven by the view projection matrix. Looking at this 3D wireframe, the numerical determinant dictates the exact scaling factor applied to the asset. Values greater than 1 physically expand the asset, while values between 0 and 1 shrink it. If the determinant drops below 0, the geometry mathematically inverts. The asset collapses through itself, effectively flipping inside out. Rendering engines use this negative determinant as a deliberate signal. It tells the software to reverse vertex winding orders for backface culling, optimizing what the camera actually sees. Physics engines and ray tracing algorithms also face the reversibility problem. When a user clicks a 2D screen, the engine must convert those flat screen space coordinates back into 3D world space coordinates. This unprojection process demands calculating the exact inverse of the view projection matrix. Our ability to physically interact with any digital 3D space is permanently tethered to the non-singular nature of its underlying mathematical framework. In practical application, engineers do not calculate thousands of variables by hand using manual Laplace expansion. Instead, they construct standalone verification engines using programming languages like Python and optimization libraries like NumPy. As seen in this split-screen comparison, the exact programming syntax used to compute these inverses is structurally identical to the theoretical math built out earlier. The execution of the code perfectly mirrors the mathematical constraints. If the determinant hits 0, a NumPy script will immediately halt and throw a singular matrix exception. Linear algebra provides the structural limits for operation across all these disciplines. The physically reversed satellite, the ungrounded circuit, and the collapsed 3D model all represent the same failure state, a determinant equal to 0. The processing of data must fundamentally remain bidirectional. The determinant and matrix inversion are universal structural integrity checks. They ensure that across any engineering reality, the mathematical path from output back to input remains unbroken.